And welcome back to another episode of Let's Learn Zig. So what we're doing today, we are going to go in deep about loops. May seem simple, but there's a lot of ways to do loops in Zig. It's actually, there's quite a lot of nuances and kind of cool things you can do with loops. It may seem simple, but we're going to go over as many as possible. I tried to lay, I'd say, a lot of the building blocks of loops in this video. Showed some cool stuff like comp time, uses or inline loops as values, and then of course just basic while and for loops. And yeah, I think the code will speak for itself, so let's just get right into it. Okay, let's get right into the first example. So we're going to start off with while loops. So a while loop is we're just going to be able to continually execute a block of code while a condition is true. So let's just show that. So we'll get and a value, we'll start at 0, and we'll just say while, say I is less than 5. We're going to do std debug print I equals a value, and then we'll take I, and then we'll increment I by 1 at the end of the loop. So what's this doing? We start I at 0, so it'll be, let's see, is 0 less than 5? Yes, so we'll print this, then we'll increment, and I will be 1. So now is 1 less than 5? Yes, and it'll just continue until this hits 5, and then it'll exit and skip and just exit out. So let's run that. And there we go. We see exactly that. I equals, didn't do proper good spacing. Let's just run that one more time. But yeah, so I equals 0 through 4. So again, because we see I starts at 0 and we're printing before, we can also just print after if we want to print out 1 through 5. So one very cool thing about Zig is you actually use a while loop to emulate a normal C style for loop. So let's see exactly what that looks like. It's very simple. And it's the closest we'll get. We still have to initialize it outside, but then you can just use this syntax, and we can do I plus equals 1, and we can get rid of this here. So now what this while loop will do is afterwards, so again, this will print 1 through 4 again, because after everything in this block executes, this little bit of code will run. So we run that, and we can see 0 through 4 again. Okay, but now let's get into for loops. So one way to actually make this a lot simpler is we'll get rid of this, and we'll use a for loop. So we can say from 0 to 5, and we use this syntax to get that I. So now this I variable is a kind of auto incremented. So it'll go from 0 up to 5, but not including. So it'll be 0 through 4 again. And now I is just that value, and this is a lot cleaner. So we run it again. You see, we get the exact same 0 through 4. Okay, so now let's actually get some numbers in here. So we can see we have 10, 20, 30, 40, 50. And let's say we want to loop over all the numbers and print them out. So what will that look like? Well, we'll go numbers. In this case, we'll say n. So now we're going to go one at a time through all of them. And now we can say number equals that, and should print 10, like all 5 of those numbers. And there you go. So we can see we have 10, 20, 30, 40, 50. And it's a very simple way to just loop over a slice. And one last thing about kind of how this looks is, let's say we want to have loop over the values, but then also get the index. We can do this special syntax to say we'll have a range, and now we'll have I. So now we can see it, the IntelliSense is actually showing us we have the U32s, which come from here, and the index, which is a U size. So we can say numbers that, and then I equals this. We can have n and I. And now if we run that, we can see 10 is at index 0, 20 is index 1, so on, and 50 is at index 4. Okay, let's say we actually want to mutate the values in a slice. What does that look like? So we're going to use those same numbers here, and we're going to get rid of this. And what we're going to do is take a reference. So again, haven't put out a video on pointers yet, but this will make more sense there. So now instead of looping over the number one at a time, we're actually getting a pointer to each number. And now instead of printing, we can do something more like this. We can do n, get the value, and let's just double it. So we'll do times equals 2. So what this does is this dot star is saying get the value at the pointer or at the address that n is pointing to, and then multiply that by 2. So let's see what this looks like. print doubled and not values, but these are numbers. And one thing I just forgot to do is that should now be a var instead. So if we run that now, and now we can see those numbers are doubled. So instead of 1, 20, 30, 40, 50, it's 20, 40, 60, 80, 100. So that is how you'll kind of loop over and be able to modify it, because we wouldn't have been able to modify it before. Okay, I brought back this example really quick because I just want to show how this kind of like putting multiple values in the for brackets is a lot more applicable than just have these two. So let's take these two slices. So we have names and ages. So we can actually do this. We can do names and ages. And as long as they're the same size, that's what really matters. So name, age. So we can say whoever this person is this years old. So we can do the name and age. And don't forget the modifier. So now we run that. We can see Alice is 30 years old, Bob is 25, Charlie's 35. And again, if we want that index, we can just do that exact same thing. And you can kind of do it to any amount as long as everything matches up. And then just show it one more time that it works. Then we have the indexes. And then really quick, I just pasted this in to show you what happens if these are different sizes. Like I said, they have to be the same size, or the kind of index range has to match up. So this has 3 items. This only has 2. What happens if we try to run it? So we get an error and then non-matching for loop lengths. Okay, so now I want to show an example of continue and break. So let's see what's going to happen here. So we're going from 0 to 10. And what continue will do is basically just say, stop where we are and go back to the start and go to the next iteration of the loop. Break will be, I don't care where we are, let's just exit this loop and it'll immediately come down here. So let's see. So we go with 0, doesn't hit either of these. Then we just print 0. So we'll print 0, 1, 2. It's going to not print 3 because we're going to continue past 3 because we'll immediately hit this and then go to 4. 4 will print, 5 will print, 6 will print. With 7, we exit. So that means 8, 9, and 10, or just 8 and 9, I guess, won't get printed, right? So if we run this, there we go. So we have 0 through 6, which is exactly what we thought. And again, there's no 3, because when we hit 3, we skip over it. And when we hit 7, we break out. So that's never printed. Okay, and I want to type this next one out just to show how we can use kind of labels to then continue to certain spots or break or continue to certain spots. So let's start with 1. We'll do this outer, and then for 0 to 3, get the I, and for 0 to 5, do J. And let's say within this inner for loop, we want to just skip to the next one of outer. We technically could break. That is one valid option here, because it'll break out of this loop and continue the next one. But if, just for example's sake, we'll do 3 and we do continue outer, it's going to say continue, but instead of continuing this kind of J loop, it's going to continue up here. And then debug print. And then we'll just print everything. And then try and guess what the output of this will be. Okay, let's run it and take a second, try and guess what the output will be and see if you're right. And let's see, so 0, 0, so that's printed all of them. But we see every single time we get to 3, we kind of go to the next one. So this is the J, so we do 0, 1, 2, and then it hits the 3 here, and then goes to the next I row up here. So that's why we never get 4 or 3, 4 in it. Okay, I'm going to paste in a much more exciting example here, which is, let's say you have the nested rows again, but you want to just completely break out of the outer loop when you're inside the inner loop. So we're going to do the same thing where we put a label, and now inside of this inner loop, if we break at this label, it's just going to immediately come down to the end. So what is this doing? We have a grid. We're kind of doing for row and column. In this grid, we're going to try and find something. So in this case, it's 5. So now if we run this, You see we found 5 at row 1, column 1, because as soon as it found the target, we stopped looking. And just to actually show like it is truly stopping, let's just do a debug print, and we'll just print out every single kind of row column that we're searching for. So do that row column, and then RC. And if we run it, we can see searching these rows, and then we stopped, right? We went 0, 0, 0, 1, 0, 2, 1, 0, and then we found it at 1, 1, and we stopped. Okay, I have 2 more things I want to show. One is going to be loops as expressions, and then inline loops, which is kind of comp time stuff, which these next 2 will be pretty brief, but I just kind of want to show slightly more powerful and cool things. So let's say you want to find the index of some sort of slice. How will we do that? Well, we can do a normal loop, kind of set of var like index u32 equals 0, and then you can loop over the haystack, and you probably want to do something like this, and then if haystack, let's say we're trying to find the value, let's actually get the proper values here. So if h equals, let's say the target is 10, then we do idx equals I, and this all works, right? This works no problem, but I want to show, and then let's just, I guess, debug it, idx, and let's print that out. And this one should actually be a usize. And if we print it, we see 10 is at 0. Let's just make sure that it's can go past that. There you go. So now this completely works, but it's kind of verbose in a way. Like there's nothing wrong with this. If you wrote this code in production, I don't think there'd be any complaints, but I just want to show a different way to do that. So let's do that right now. So let's now grab the index, and now we're directly assigning a for loop to a value. So that's what I mean by loops as expressions. We're going to go through the entire for loop, and whatever values returned or broken out of it, we put in the idx variable. So, and then this is going to look very similar to what we have, haystack and that, and then we do h and I, and then if h equals 20, just like we have there, we can just do break I. So now let's just comment this out, and we should get the exact same thing. And then one other thing I forgot to add is you have to do else null. You have to kind of have a catch. Like if if nothing is broken, if we don't do any sort of break statement with a value, it has to hit an else case. So if we run that, and in this case, we know that it's going to have a value, so we can just grab it right out of it. And there we go. We get index 1, just like before. And then we can go back to 0. Let's say it's not found, so it's going to be null. So we actually only want to print if idx does not equal null. Then we print it. So in this case, because it's not going to find it, it shouldn't print anything. And it doesn't. And then if we go back, let's do 50 this time. We run it, and then index of 4. Okay. And now I want to show we're going to get into the comp time and inline for loops, which I think are pretty cool. So if we look at this code, we have a tuple, but we see the tuple has, let's see, a U32, a string, and a Boolean. If we do this normal for loop, let's try and run the code, we see it compile errors, and we see unable to resolve comp time value. So that can make sense because these are all known at comp time, not necessarily, or the types are kind of have to be declared at comp time, and it just isn't able to resolve it properly during runtime because they're comp time values. So how do we solve that? All we have to do is put the keyword inline in for, and this is essentially in other places like doing comp time, but for the for loops. So now if we run this, we see we get the values. And in this case, this is the string just put as bytes, as this is any, so there's no actual S specifier, so it just prints out the bytes. Let's do a slightly more interesting example. Let's say we have this point struct, right? And we would just want to print, let's say, some metadata about it. We're gonna do that inline for std meta fields, and then we're gonna pass in that point struct and then get each field. So now we can do a debug print s and s, and then we can get field.name and type name of field.type. So now if we run this, we see we get X, Y, Z, and they're all F32s. And if for some reason, let's say this was an X64, or in this one was an I32, we can now run that again, and there we go. We see we're now printing more metadata and information about the struct. So this is kind of meta programming. We can see it gets a little more complex. It's worth comp time. Again, I'm going to have a full episode on comp time probably pretty soon. Yeah, that's all the code I want to show today. I just want to show there's a lot of different ways to use loops in Zig, and I tried to cover as many as possible. There obviously way more you can mix and match and do things, but hopefully I gave the building blocks and you guys can continue on. I hope you enjoyed the video. I think, like I said, loops may not be the most exciting or crazy thing in a language, but they're needed. You're going to use loops all the time. They're important parts of the feature. So I tried to go and show a lot of different cool things about them. So yeah, I hope you guys enjoyed. And as always, let me know if you're enjoying the series, drop some comments, tell me what you want to see. And if you want to chat more, Discord links always down in the description. But yeah, just have a great day.